All right, glad to have Simon DeDeo from Carnegie Mellon and the Santa Fe Institute. He's going to talk about a change of title.
A change of title. Well, this is the more aggressive title. So, I'm usually at Carnegie Mellon, Social and Decision Sciences. One of the things we work on in our lab, we have a whole bunch of research projects going. Some are theoretical, some are experimental. But our larger goals are probably summed up in this image. So these two things here, this is my office in Santa Fe. These two things here, I shouldn't have these at all. I should never have had these on my desk. I don't have them anymore. They were sort of stolen from the University of Michigan's Archaeological Museum. These are what we call ration bowls. They're about 5,000 years old. They're made out of clay. They're the first evidence we have of state formation. So these are actually, this is how you got paid. Some sort of nascent nation state would try to do some big project. They'd have what's called corvée labor. You'd work for the state, and you get paid in barley. And what they would do is you take your ration bowl up to the supervisor, and he'd fill it up to the top with barley, and then kind of make sure you all had the same amount. These are like the junk mail of archaeology, right? So when you start digging in a place that has these, you find hundreds and hundreds and hundreds, which is sort of why no one noticed that these went missing for a while. In the back, well, actually, one more thing about this. It's fun. These are clay. They're very easy to make. If yours breaks, you borrow your friends. You dig a hole in the sand, fit your friends in, take your friends out, put clay in, and punch it down, and just kind of smooth it out. One of the things that's fun is in the bottom here, you can run your hand in the fingerprints that are left by that person. So this is contact across 5,000 years. Today, right, this is what we have. We began here, we ended up here, and so the question is, how on earth did that happen, right? Within a time span that is a blink of the eye from the point of view of biological evolution. There's really no evolution that's possible in any real sense on that kind of time scale. We managed to utterly transform our environment, to transform our cognitive and our social worlds. And our goal is to understand how that happens. And we work on different timescales. We work on some very short ones, particularly in the internet era, and we work on some much longer ones as we go back in history. Fundamentally, to answer this question, how to get from here to here, you have to answer the question of how novelty, how new things enter the world, how new things enter the story. And what that means is that we are often in a position of studying how people change their minds, how people both create new things, but also how other people come to accept them. That's our basic problem. And in studying that problem, we ended up in some really interesting places. We ended up in some interesting places theoretically and philosophically, as well as empirically. One of the things that I've come to believe from our empirical work, and also from some maybe more philosophical reasons in terms of how we even justify our explanations. One of the things I've come to believe is that rational choice theory, and in particular its basis in utility theory, is fundamentally unscientific. It's unscientific. It may be satisfying to you as a story about the way the world works, but it is not a way to explain why the world is the way it is. In particular, I believe that we should be trying to construct a theory of human behavior, accounts of human behavior, that don't simply require us to specify the utilities agents have out the other side. So of course this puts me in opposition to like half the people in my department who are very gracious in letting me work on this. Before I get to the actual stuff, usually this slide comes at the end, but sometimes we don't get to the end. So these are some of the people I've worked with. I'll begin here in the theory, and this is work with Zach, who's one of these superstars we get at CMU from time to time. And then Alexander, Rebecca, Jenny, YY, and Elise. All of these people here, I've been lucky enough to work with on some of the empirical results. So I'm going to give you some philosophical reasons to think that utility theory is bullshit. I'm going to give you some mathematics that tells you what to do with that fact. And then out the other side, I'm also going to give you some accounts of human behavior, some observational features of the world that might lead you to believe not only that utility theory is not working, but that we may actually have a handle on a different way to talk about why and how people do the things that they do.
So are these people that disagree with you in the Department of Economy?
Yes. Yeah.
I don't think you have any economists in your audience here.
That's good.
So you may be preaching to the choir.
Well, we'll see, right? And in which case this will be a more fun talk. There are a couple analogies. We often talk about, I should say, right, there's a porous boundary between these things. And so the quantities that Zach and I work with are also the quantities we measure in the real world. It's a very satisfying and reasonably tight connection between the mathematical formalism and the things that we try to infer from data. One of the standard paradigms for talking about cultural evolution is this analogy to biological evolution. So change in culture is made analogous to change in the phenotype of an organism or of a population. If you're a biologist, you know there's this sort of fundamental fact, right? You have some plant at time t, you have some organism at time t, it's got all these features. The organism can't like jump up onto a 3D printer and kind of copy itself, right? In order for this plant to survive until the next generation, it has to squeeze things down what we call the genetic bottleneck, right? So there's an enormous amount of information in the phenotype itself and the structure of the plant, right? If you were to describe all of the systematic properties of that plant, where the vacuoles are and all that, right? There's an enormous amount of information that has to get crammed down this really, really tight and small channel in order to propagate forwards. That's true for you and I as well, of course. It's your gametes that provide this channel. Almost everything gets dumped out until you get to the next step. Culture is the same way, right? So here's some cultural practice. This is some work from a while ago. This is like some trial at the Old Bailey in the 18th century. This is some cultural practice, and when we look at the world, we look at what people do. It's incredibly complicated. Not just complex, but complicated. There's all sorts of details. There's the way they wrote this. It's the names of the people, the particular details of where this particular crime was committed, right? At the same time, there's some underlying cultural patterns. And in some sense, what we consider a cultural pattern is whatever can propagate through an equivalent bottleneck, which is the cognitive bottleneck, right? In order to get from one generation to the next biologically, you squeeze it through this mechanism. In order to get from one time of culture to another, you squeeze it down this bottleneck here. In other words, in order to do social science, you also have to do cognitive science. In order to do macroevolution, you have to know how DNA and ribosomes work. The problem with the cognitive bottleneck, or perhaps maybe it's a feature, not a bug. The problem with the cognitive bottleneck is that your brain doesn't represent to you the world the way it is. It represents to you, it gives you a theory of the world that is constantly being massaged. You can think of it, and here's a great example. This is a standard optical illusion. There's plenty of these. If you are sort of a neurotypical person, this square here, A, will look darker than this square here, B. Right? You know it's coming. They're exactly the same hue. Right? And yet it's impossible to dispel this feeling here. Right? If you just saw this and you were asked to describe it, you'd report this as lighter than that, and so forth. Right? So what's going on here? Well, you're getting this huge pile of information that's coming into your retina, right? And that's propagating further and further up into your visual system, into your conscious awareness. At each step, an enormous amount of stuff is getting thrown out, right? So the exact pixel luminance here and here, that at some point in your visual system is being processed reasonably accurately. Right? If we were able to detect where these photons and these photons were falling on your retina and measured all the ways in which it's triggering electrical impulses further down, we're gonna derive correctly that these have the same luminance. But by the time it propagates further upwards, this image has been transformed into a theory of the world. It's a confabulation that happens in your brain. Now this confabulation is baked in pretty hard. Right? These are not culturally variable. People have tried. There's some visual illusions where we thought they would potentially be culturally variable. So there's a great one. It's the convergent lines. Let's see. It's the convergent lines one. So I will draw it as thick as I can. Here are two converging lines. Here's two bars of the same length. If they converge like this one will look larger than this, even though, in fact, if you measure them, they're the same length. We had this theory for a while that this was something that you learned. Oh, thank you. I'll redraw this. Here's the illusion. I'm not very good at this, it turns out. This one will look larger than this, even though they're the same length. And for a while, we had this idea that this was actually culturally programmed. It's because we live in environments with lots of converging lines, because we build roads and buildings. And so anthropologists went out and tried to establish the existence of this illusion in other cultures. And it turns out it doesn't matter where you can grow up in the jungle, where you have no long sight lines and lots of wavy things. You can grow up in the desert. Everybody has this response, right? So this is pretty hard-coded in. Here's another example. And actually, before I give you that example, I'll maybe tell you a little bit of the underlying theory. This is the analogy from machine learning, right? So it turns out we don't reason symbolically. GoFi, good old-fashioned AI, turned out not to work. And it turns out that, in fact, the magic, everything we wanted in the 1970s, HAL 9000, all of that magic actually ends up being just take a neural network and scale it up a few more orders of magnitude. This is one system that gives you this sort of machine version of the cognitive bottleneck. This pattern, this way of arranging connections in a network, the sort of topology of the network, turns out to be extraordinarily successful. So this is a bit of a schematic. The way to think about this is, okay, on this input here you have, let's say, 1,000 neurons or pseudoneurons, right? You have 1,000 entries here, and those 1,000 entries might be all the pixels in an image, right? So if I do that, like here's an image, like this is Dave Feldman, a colleague of mine, right? So I take an image, and there are 1,000 pixels, I feed it in here, and there's some magical set of functions that you find because you have a grant from Google, and that magical set of functions will map these 1,000 elements into, let's say, 100 elements. So what's happening is that it's doing some transformation on the image, but it's also throwing out information, right? It's also, in fact, tossing out an enormous amount of information. You have 1,000 numbers here, you have 100 here. You can't reconstruct this from this as long as the numbers are discrete, which they are, right? And then, okay, you just up the ante, and you're like, fine, I have 100, I'll go down to 20. Right? So I've mapped 1,000 to 100 to 20, and there's some magic here in figuring out exactly what those maps look like. That's the training of the neural network. You get down to this bottleneck here, and then what you do, and this is what an autoencoder is, right? Then you actually re-expand it. You're like, great, take that 20 and turn it into 100 again. And take that 100 and turn it into 1,000 again. And your job, neural network, is to reproduce as accurately as possible the input image. So you're setting all of the numbers here, all of these functions here. You're squeezing the image down the bottleneck. You're re-expanding it, and you want to get the original image back. Now that's impossible. It's impossible to get exactly the same image back. You've thrown out too much information, right? You've thrown out maybe 99% of the information. But there's an enormous amount of structure in the world, it turns out. Like, Dave has a face. He has edges around his face. There are big blocks of color, right? The average image, if you just sort of took a random set of pixels you sampled from the space of all possible images, the average image would look nothing like the real world. So people like Dave and you and I live in this sort of massive submanifold, this incredible compression. And all the autoencoder is able to do is work out some kind of simplification code. And maybe at some early level, it takes all these pixels and decomposes them into lines. And then a little further down, it might even decompose the lines into things like eyes and noses and where your forehead goes, and even have some logic about that. So in the center here, you might imagine that this is the confabulation that's equivalent to this thing here. Right? You think you're seeing this. Actually, you've gotten only a tiny bit of the information in the world, and it's contained in this sort of compressed, lossily compressed code. One thing that you can do once you have this bottleneck story going is you can kind of go in and tickle this internal, like the neck of the bottleneck, you can tickle it, and you can produce images of Dave that like no one has ever seen, right? So this is now a new game that people play in like if they do work at Google, right? They take a bunch of images, train, and then they can produce like George Clooney's that never existed. They can produce people who've never existed. And they can do this because this code actually contains the logic of the environment. It contains a theory about the world, and the ways in which these things fire here tell you a great deal about the structure of that world. If you're a Bayesian, somehow implicitly this is a heuristic model of the causes and the structures that you encounter from day to day. To sort of drive home this example, so you all have, I give you this handout here. So have people seen their blind, have you seen your blind spot, Harry?
How could I?
Well, here you go, right? It's a little bit like the optical illusion we had before. So I'll do one for myself. You can do this at home. So your paper will have an X and a dot, right? So put the X on the left, right? Okay, hold it out like this, right? So the X is on the left, hold it out like this. Close your left eye and look at the X and move that paper in and out. And what you should see for a pretty wide range is that dot disappears. So from here, for me, I'm looking at the X, the dot has disappeared. I move it further and further out, and in fact, only there does the dot reappear. People seeing this effect? Right? So I wonder, it's a question, when in the history of philosophy did we discover the existence of the blind spot, right? There's just this gigantic patch that's missing from our vision. And it's the reason it's actually our eye is terribly designed, right? So if you have your iPhone, you have the light-sensitive photodetectors here, and then the wires come out the back. We were really badly designed, so we have our little light-sensitive detectors, and the wires come out the front. Like, great, right? So they have to snake around, and then they have to come out, so there's this plug that sits in the back of your eye, and that plug has to go out. So there's actually this absence of detectors here, right? So there's these huge chunks of your environment that you're not seeing, but you've never noticed it, right? So if I'm looking, I'll do the same thing, right? Actually, I'll do it this way. If I'm looking here, Harry's in my blind spot right now. Like, I'm not getting any Harry data, and yet I have the feeling that he's there. I don't see some black spot, right? My brain is painting in what it thinks should be around in this space here. I don't see Harry without a head, for example, right? I just see like Harry-like stuff. You can, as sort of a milder version, you can do the same illusion and just, photocopy it onto a newspaper. And when you do it and the dot disappears, you don't see white there. You see sort of newspapery-like stuff. Like your brain is like, don't worry, we're gonna confabulate what is probably there given our priors about the way the world works. Okay. So, so what I've given you so far is an account of human perception that says your brain is rejecting or throwing out all the information it doesn't need, and it's fitting it into a model that's particularly strong. Right? It's strong enough to reconstruct big chunks of the environment. This brings us to a problem, which is that if your brain is constantly compensating for weird stuff, right? If it's constantly trying to work out what should be there, when you actually feed it weird stuff, when you feed it stuff that breaks the priors, when you feed it stuff that you're not expecting, right? How do you ever get that input through? Why do we ever perceive things that are new? Another way to put it is, the ways in which our brains seem to work is that we're constantly tossing out things that don't fit the pattern. That seems to be something that's fitting into our encounters with the world. And so anything that breaks that pattern, anything new, has not just a, let's say, social barrier, like why are you being so weird, but literally a cognitive barrier. We don't see most of what's happening, and so when somebody goes out there and tries to break a pattern, if they do something new, if they behave differently, we edit it out. So there's a pressure sitting in there. It's almost an epistemic pressure that's sitting inside of us. And it's one of the things that if culture, let's say, is going to change, if social practices are going to change, right, that's something that we're going to have to overcome. So this is not the story that's usually told about the world, right? Here's how we're taught to think about human behavior and human action, right? It's a fundamentally dualistic story. And so this is going to be the negative story. This is the bad, unscientific thing. Descartes is the original dualist. There he had the mind-body dualism. The dualism we have today is a belief-desire dualism. So the standard story is the way you decide what people do is you figure out what you know or what they know, right? And you figure out what they want. So I know some stuff about the world, and there's stuff I want as well. So given what I know and what I desire, in other words, given an account, let's say a Bayesian account, and given, let's say, an account of desire that satisfies some axioms, like let's say utility theory, those together, right, two different units of quantities, utils and bits, right? This is measured, this is an informational quantity, this is a desire quantity, and util is the unit of desire, right? I combine these two things, and out the other side, I can get a story about what you do. So this is rational choice theory. I think it's fundamentally unscientific. And I think that you can get away without this. And in fact, you ought to get away without this. Every time this is something I began to realize when I was teaching at the Santa Fe Institute in the summer school, right? So I would give examples of some really interesting social phenomena, right? So one of the great examples is a paper called A Fine is a Price, which comes from the Haifa daycare story, where they found, for example, that if they imposed a penalty on parents for being late to pick up their children, if they fined parents for being late to pick up their children, parents were late more often, right? And so these stories are trying to get at, okay, maybe the standard microeconomic account of how people behave fail. Every time I give an example, there'd be some guy in the back, right, who was doing his PhD in economics at UChicago or whatever, right? And he'd raise his hand, he'd be like, I can explain that. Right? It turns out, this is an incomplete contract, and I was like, this revelation of information, and by stating the price, you've told me it's something, right? So I realized there was nothing that people couldn't explain by postulating some sufficiently weird set of desires. I challenge you to do this, right? I challenge you to come up, and the only job here is that this has to, you have to have totally unrestricted complexity on this side here, right? But from that, you can make people do anything, right? These are, I say they're dualistic. One reason to say they're unscientific is because you can just overfit desires. Desires have no constraints. Like, you can ask people what they want, but anybody in marketing will tell you they don't truly tell you what they believe, right? So you have to go observe what they want. It reduces down to, I desire what I desire, right? I'm doing what I want to do. Right? Under constraint, right? There's a similar kind of paradox, there's a similar sort of emptiness in the case of evolution, right? I'm fit because I reproduce, and I reproduce because I'm fit, right? There's no value add here, right? We know that people have drives. We know that people want to do things. That's a fundamental feature. And all utility theory is saying is the drives you have are the drives you have. What we'd like to do actually is derive those drives. We'd like to figure out what drives people, as opposed to watching what they do and sort of, by hand putting in all the desires that they have. Okay. So, yes?
Can I go back to this slide about dualistic theory?
Yeah.
And the previous one again.
Oh, yeah.
So, I didn't quite understand the motivations here about the critique of utility theory based on flexibility and stuff. But before that, I think what you mean on the left-hand side is not what you know, what you believe to be the case.
Well, yes. Okay, knowledge or belief. Yeah. Okay. So, what you believe about the world. Yes.
Right, I mean,
yeah.
It's like a precise sense.
Yes, that's fair. Yeah.
Knowledge implies truth.
Yes.
Knowledge is factive.
Yes.
So I think you just mean probabilities here, but not facts.
Yes. Yeah. Or what I think I know, right? Or what I believe. Sort of generically speaking, my epistemic states. Right? Yeah. And what rational choice theory, what microeconomics does is it postulates this other thing, not just epistemic states, but this other set of things called like wanting states, right? Urge states, right? And, like, what's the evidence for the want to obey these following axioms that seem like good axioms of rationality, right, then, okay, we should be reasonable. In some sense, consistency is a feature of rationality, right? On the desiring side, on the utility side, right, you might put constraints on them. But those constraints can only be constraints that themselves reduce down to values, right? I ought to value this more than that. And then you say, well, where does that value come from? Why are those desires better than these desires? Why should I want these desires more than those desires?
There's a theory of rationality and ethics. It's not a theory of, this utility theory by itself.
So true. I mean, once you get to the normative level, yeah.
Yeah, you can get a meta-ethical story of how utility theory get grounded in the true values in the world.
Sure, sure. And okay, so that's the normative case, right? And I guess if you had a sufficiently strong normative case, right, this, you would sort of, a super intelligent AI that did this would be stupid.
That's right.
Right.
So you say that this is not the definition of intelligence here.
Right.
In the sense that if you have voluntary desires or voluntary actions to hack your utility function, no matter what it is,
Yep.
like say killing babies more valuable than protecting babies,
Right.
then it's not intelligent.
So I think, it's it's funny, right? So maybe hanging out with all these kind of, artificial intelligence is going to eat the world singularitarians, right? They make this strong split between intelligence and morality, right? For them, it's the value alignment problem. This machine is super smart, and smart in some ways that we might think about, like, let's say, take Kaczynski was smart, like great at creative mathematical work, right? And they're worried about, okay, they make this split between these two things, and they say, well, the problem is that the machine can be super smart, but it could also be, let's say, evil, right? Or it could be like the Big Lebowski, right? Lebowski could just sort of hang out and addict itself, become a wirehead, right?
It's reduced to be against either,
Yes.
intelligence definition
Well
or
done.
your theory.
Yeah, that's wonderful. Yeah, exactly. So you can either say this is the problem or this is the problem, right? I like to have a notion of intelligence that intelligence itself is a natural kind that is a non-normative, that has a non-normative feature to it. But if you say there's a normative feature, you have a totally different outcome. So okay, if we accept that the way to do things is not to addict yourself, right? That it's not just that utility theory can it's like paper, you can write anything on it. But we maybe even buy the idea that if you push this story far enough, you enter these strange paradoxes where the most intelligent thing to do is to use math in a sustainable fashion. We can maybe get out of this not by denying the existence of drives. We're obviously goal-oriented creatures, right? So we don't say that there's nothing we want. We just sit around and we know. But I suggest we could actually have a monist theory of behavior. We can reject this dualism of belief, epistemic state, and again, this weird thing, which we call like the wanting or the desiring ghost, right? Instead, we can do the following, right? We can start with what you know, right? Okay, right, Spinoza versus Descartes, well done, right? And in fact, what you know gives you what you want. This is the prior, right? And from this you get this. And maybe this is a way, like if you're a philosopher, you sit down and you form enough beliefs and you realize I ought not to eat babies, right? So maybe this is where our knowledge of normative rationality comes from. Somehow what you know gives you what you want. And from that, what you do, you get what you do, right? So there's this pathway and there's this pathway, but there's only one origin, right? Which is in contrast to the rational choice, the microeconomic model, where there's actually two substances sitting up here. Here, there's just one origin, right? So we have this epistemic drive, right? And okay, maybe there's some, depending on how hardcore you want to be, right? And some people take it all the way. This might be the truth, but maybe you're not ready for full hardcore monism, right? You're not like Karl Friston or something, right? So maybe just sneak in a little bit, right? So like, I have all these epistemic drives, but like every now and again I take a break and eat, right? So this could be like dim or strong, depending like how much guts you have, right?
You started early in your talk. You were talking about culture.
Mm-hmm.
Is this what you mean? Is culture playing a role here? Is this the external forcing?
External forcing could be cultural. It could be purely material, which is often what we think about. You know, it could be I'm going to get like, you know, I have to eat because I'm going to die. I'm not all the way here, but I think that there's a really strong distinction between these levels. So social behavior, for example, I think really does look like this, right? I think the behaviors that we're interested in as economists, social scientists, psychologists actually have this monistic structure. But can I get rid of, let's say, the fitness function in evolution? Maybe not, right? So some people say they can go all the way down, right? They can look not just at the emergent properties of human behavior, but in fact they can get down to a biological level, and like your ribosomes are just sort of epistemically driven. So that's a more extreme version. I'm happy to stick at this higher level, and yet that's, I think, radical enough given the state we're in currently. Yes?
How is this related to state-dependent utilities?
This is great, yeah. And so actually another this is a colleague, Russell Goldman and George Lowenstein talk about belief-based utilities, right? In all of those cases, you're sticking in a second input here, right? You're putting in over and above your knowledge states, you're also sticking in a set of independent parameters or independent stories that come from this desiring side.
That seems to be what the external force is doing.
Yeah, you could, right? I mean, let's say, maybe I can just like back this out, right? This is what I believe about human behavior, right? Now, at the level at which we work psychologically and sociologically, if I go all the way down to like measuring your physiology, right, you might be too tired, right, for this all to work. So there's some external, you have some biological constraints, right? But these come in at a much lower level than the kinds of behavior we're interested in describing. So how do we go from here to here? Like, how does this mechanism actually work? How do we actually make this roll forward, right? How do we go from, you know, sort of unscientific dualism to the true monistic theory of the world? Well, one thing, you got some function f, and the function f tells you what you're going to do, right? And the standard thing here is that you've got some set of beliefs, right? Let's say you're a Bayesian, so you've got your vector of beliefs. And you've got your vector of, like, desires, right? Here's your ghost in the machine. And to get from the sort of red to the blue, all you do, right, is just swap out u for some function of p. That's it, right? So two things, one thing, and now it comes down to, like, what is g, right? What's going to be our function if we want to sort of play out, if we don't want to dump all our mathematics and start from the beginning? How do we replace this, and what ought we to put in here instead of that free parameter, that sort of infinitely complexifiable story? What should we put in here? What should be our g? So, I said that, I've told this picture here, what you know gives you what you want. There's the sort of extreme case, right, which is that we're all sort of true Socratic philosophers, like our actions are entirely driven by the desire to learn things. That's extreme, right? I don't think we have to go that far. But what this does imply is that what we do, our actions, are related to changes in knowledge states, right? What we're doing, what we do is in part determined by what we know, but also determined by ways in which our knowledge might change in the future, right? Otherwise, if the g of p never changed, if it was a constant, then we could just drop it out, and we wouldn't have this term here, and now all of a sudden we've lost the notion of a drive. So, what might an epistemic desire look like? What might an epistemic drive look like? So I'll tell you the brief story of how we've, in the past, combined information and utility theory. And then I'll show you a way that people have swapped out the utility for a function that's, to a function of purely epistemic states. So first we'll do the rational choice story. So this is known as rate distortion theory. Rate distortion theory says there's some facts in the world. I want to gather those facts. I have some channel that they travel along. I can't get everything down that channel. I have to throw some stuff out. I have to have an encoding that's a lossy encoding. How do I choose that encoding? Well, what I want is, I want to get a lot of information about the world. I can't get all of it. I have some rate limit. And so what I'm going to do is I'm going to gather the information that's most important to me. And in particular, what I'm going to do is try to minimize d, which is the distortion, which is just the negative of the utility function. There are some mistakes that it's really bad to make. There are some encodings that it's really bad to use because they'll mix up things that I don't want to mix up, right? So this is an example of how our cognitive life might be described both by an information theoretic or epistemic fluid, and also this utility or desiring fluid, right? So the encoding story might be, it's okay to mix up tigers and lions because they're both bad, but you shouldn't mix up lions and trees. If it's a lion and you think it's a tree, that's very bad, so don't make that mistake. So that's rate distortion theory. Then some gurus came along and invented what's called the information bottleneck. The information bottleneck is almost exactly the same as rate distortion, but now it gets rid of utility theory, right? So it looks like ghost bad, right? Now we have three things. Instead of learning about the world and taking actions, we now learn about the world, we take actions, but in between we have a model of the world. So you can think of this a little bit like the autoencoder, right? So the input here is the world state, the Y is the mental state, and the output here is the action state. This one here said, given the state of the world and some encoding, right, what I want you to do. Down here, given the state of the world and some output, and given this internal model, so now this is your epistemic state, right? What should you do? And they take the same quantity here that you're trying to minimize, so there's an epistemic quantity you want to minimize, and a utility quantity that you want to minimize. Instead, you now have two epistemic ones. We've swapped out this u for another function of p. So you can think of this now, there's a cost of information, but instead of some utility function, we have another bit, we have another information value, another epistemic value. So this is an example of how we're already starting to do, how we're starting to reject utility theory in building models of, in this case, human perception. Right? We don't observe the things that are important for us to observe. We observe the things that have particularly useful, or particularly, I should say, particular features of their cognitive structures. That's the fundamental drive. So what I'm going to do now is walk you through some of the quantities that I think play a role in that G. Right? So I've told you, okay, we should think about describing human behavior in terms of not P and U, but P and some G of and some G of P. Right? So we should talk not just about we should reject talk about desires, but if we reject talk about desires, then the question is, what do we replace them with, right? The function f has two entries, it has two arguments, so what do we stick into that second argument? The quantities will be information theoretic, so I put some of them up on the screen. I'll now walk you through a really simple one. It's called Kullback-Leibler Divergence, so Harry has already seen part of this. First, I'll introduce the notion of entropy, or sometimes just called uncertainty in information. Who here has encountered entropy before? Okay. Great, so the philosophers, okay. So here's the story. We'll begin with this really simple example. If you are a parent, or you at one point were a child, you may have played the game 20 questions. So the game 20 questions, like you have this parent, you have a child, the parent has something in mind, right? The parent thinks of, let's say, some object, some noun. The child has to figure out what's in the parent's head. In order to do that, the child asks a series of yes-no questions. The goal of the game is for the child to figure it out. The challenge is, what are the questions to ask? So just to make this really concrete, I know Harry has already played this game with me with the undergrads, but will you play this game with me again?
Sure.
Okay, so I have something in my head, right? And, okay.
Does it swim?
No.
Does it fly?
No.
Is it a sheep?
No.
Okay, we can. I didn't get it.
No, you can't keep playing for
I didn't get it in 3.
No, you didn't get 3, okay. So,
it was an animal, right?
yeah, but you knew that from before.
Yeah.
You'd already gotten some bits down the channel. So these yes-no questions, right? So the joke is, 20 Questions was a game on Polish communist television in the 80s, right? So this is why communists should not run game shows. And then the joke is, right, okay, so it's like the plumbers union comes and it's like, comrade, 20 questions. And the joke goes that they had to stop the program when the mathematicians union showed up. And the mathematicians went there and they said, okay, does the first letter of the thing you're thinking about fall in the first half of the alphabet? No, okay. Does it fall in the first half of the second half of the alphabet? Yes, okay, right? And with a strategy like that, you can actually narrow it down pretty quickly, right? If you look kind of closely at the encyclopedia here, if you pay attention, you'll see there's kind of more entries in the first half than in the second half, and so maybe you don't want to split it right at letter 13, but like maybe a little earlier, right? The intuition here is that there's better and worse ways to play the game. And the better and worse ways depend upon the system that you're interrogating. I'm trying to get information from the world. The way in which I interrogate the world depends upon the nature of the world. Right? So I have, let's say, some encoding. Here's the example that's a little simpler, that'll give us a way that will just get you to construct an optimal code. So imagine you're playing 20 questions, you're playing it against your father. Your father thinks of trees a quarter of the time, birds a quarter of the time, cars half the time. If you want to get this game over as quickly as possible, which question should you ask first?
Is it alive?
Is it alive? Yes. Tricky, right? An equivalent question that would split the set equally well would be, is it a car? Right? Because if it's a car, it's super tricky. Is it a car, right? Because if you ask that question, half the time the game's over. You're done in one question. If the answer is no, unfortunately, you have to ask another question, right? So here's one, is it a bird? Or it might be like, does it fly? Or does it have a heartbeat? And depending upon that answer, now you know for sure, right? Because if you get, let's say, no and no, okay, you know it's not a car and not a bird, so it's got to be a tree. So the average number of yes-no questions you needed to play that game against your father was 1.5. The magical story of the world is that given any probability distribution over what the person has in their mind, you can work out the number of yes-no questions on average for the optimal script without constructing the script. And it's this magical formula here from Claude Shannon in his paper from AT&T Bell Labs way back in the day, right? So you got this answer that Dad has sort of 1.5 questions in him. Questions, if they're yes, no, are called bits. Yeah, sorry, do you have a question?
The hardest part of this game is certainly to figure out this frame in which you should consider, right? Because how would you know that those are the three things?
Exactly, yeah. The challenge here is not this part, but what's here, right? What are the things that Dad has in mind and what are the probabilities of them? Like, how do you learn, in other words, how do you learn the world?
To me, the probability is even a construct. It is a consequence of other things, such as what, maybe your dad's epistemic states and stuff. Like, I think if you could even conceive what are the possible things that your dad is thinking, then you have a fair chance of a game in very short. Like if I could know what's the category or sort of the limits at which.
Yeah, if you know the category, for example, the game will be over quicker, right? If you know I'm conceiving of animals.
But this is the same as if you do probability modeling. If you don't know what is the state, if you don't know what is the support on which you're looking, there's no chance of even constructing a probability model. Right?
Yes, absolutely. So another way you're saying, like maybe just to flip this around, right? Information theory makes sense, let's say, in a Bayesian context, right? So things that the limits of Bayesianism in describing humans' epistemic states are also the limits of information theory. So for example, the challenge of figuring out the support of your father's belief space. Yes, Harry?
But is there always a kind of a unique answer to this question? I mean, so in asking you these questions, I mean, I have no idea what you're thinking. So I mean, I happened to ask you earlier whether it was an animal, and I got lucky, and you said yes. But I mean, I don't know what kind of animals you know about, and maybe I've never heard of it before. So, but if I were to just guess right away, it took me one question. So does this distribution, this 25, 25, 50, is that assumed to be the actual truth of what he's thinking about, or what I think he's thinking about?
So you can do either, and if you do one, you get one interpretation of information theory, and do the other, get the other, right? So this could be like you repeatedly encounter your dad, right? You're playing this game over and over again, and he's a stationary creature, and so this is the fraction of the time he does these things, and then the answer you get out the other side, 1.5, is on that very long car journey, on average, how long was the game? How long would the game take, right? So that's your kind of frequentist, like out in the world thing. You can make it subjectivist, and then all it is like, okay, God, this is what I think Dad's going to do. I'm going to construct the optimal question tree for him under the assumption that I get the probabilities right. How many yes/no questions is it going to take? Right. So it just now becomes an expectation value, a subjective expectation, as opposed to something that you'll see empirically in the world. And again, like the limits of my Bayesianism are the limits of my information theory. Right. That's there should be, you have a different model here, right? You have a different model of people's epistemic states, then you're going to have a different information theory, which is kind of a cool thing to think about, potentially. So you could plug this in, it's pi, log base 2 pi, right? Sum over all the possibilities, right? So this is your little Bayesian thing. Claude Shannon came up with this in 1945. It's an amazing paper. It just keeps going, and it does basically everything in information theory, including, I think, rate distortion. So it's an amazing paper. Markov chains, a study of natural language. If you're a computer scientist, this is the encodings that sit inside, like if you zip a file. So this is what we call Huffman encoding. All you have to do is turn the y's and the n's into ones and zeros, and then I can encode in the maximally efficient way a series of results from the 20 questions game. So that's a computer science version. We need one more thing, right? So I told you how to compute uncertainty, or how to compute the average number of yes/no questions. We only need one more thing, which is what happens if you bring a model of the world to the world, but the model is incorrect. So explicitly in this case, what if you build an optimal question script for your father, but use it on your mother? Right? So your father thought of cars half the time, right? Hey, your father's an Uber driver. Your mom thinks about trees half the time. She's like a theoretical ecologist. If you knew it was your mother and you knew this, you could construct an optimal tree that was over in 1.5 questions just as much as your father. But if you bring the wrong picture to the world, if you bring the wrong script, right? So here's the father's script. If you bring the wrong script and use it on your mother and let's say play the game over and over again, something is going to go wrong, because even though you should take only 1.5 questions, you will discover that in fact you take an extra quarter of a question. There's a failure in your model. And you quantify that failure in the model just as much as you quantify the amount of bandwidth you need to build that model. You can compute this using a formula. You don't have to construct the optimal question script. You can also compute this. This is this great quantity. It's called Kullback-Leibler Divergence. And now it just has two terms. One is your theory of the world. That's one distribution. The other is what actually is in the world. So this is another quantity. This is going to be G. This is going to be a replacement for a desiring drive. Yes?
No.
Okay, good. This shows up everywhere. It shows up in computer science, like coding failure. It shows up in cognitive science, so it seems to track, for example, where people look on a screen. So if you imagine like you have some movie playing, and sort of in different parts of the screen, you build a model of what's happening in those pixel values. The places that are hotspots for Kullback-Leibler divergence are also the places where the eye goes. It's kind of miraculous, right? Your eye doesn't go to the places that are uncertain. It goes to the places that are violating its models, that are violating its beliefs. It doesn't look at the random stuff. It doesn't look at the static. It looks at, for example, the place where the static becomes a pattern, or the pattern changes. So, you know what Kullback-Leibler divergence is, so I'm now going to give you three forms of G, right? And again, I'm dropping all the utility theory out there, and I'm going to try to talk about what people might do in cases where their desires are now functions of these probabilities. So number one is going to be Do you build the super collider, or do you build a telescope? The next one is going to be a set of theories that come from this guy Karl Friston in London. And the third one is going to be the Super Mario story, which is the story that comes out of the machine learning world. Right? So let's begin with LHC versus astronomy. This is an example, in some sense motivated by an old, somebody, well not colleague, somebody I encountered back in my physics days. So this is Sabine Hassenfelder. So Sabine tells the story like, we spent all this money building the Large Hadron Collider. It was a really dumb decision, right? Because lo and behold, we discovered exactly what we thought we discovered. In fact, they called this the nightmare scenario, which is a bit odd, right? The nightmare scenario became true. Sabine is like basically saying, everyone's now saying it's not the nightmare scenario, but it is, right? Nobody wanted this to be the case. It's a little odd, right? Because, well, we know we're right. Like, why weren't we happy to be proved right? So let's tell this from the point of view of epistemic drives, right? So particle physics, LHC, its job was to discover the Higgs boson or detect it. Everybody knew they were going to find the Higgs boson, right? All the models that said they wouldn't were like super contrived. There was no reason to believe them, right? It's 99.9% certain. That was our prior coming in, right? In astronomy, which is where I was instead of particle physics, astronomy, we had like way weaker priors. We didn't really know what was out there, right? So my old advisor, David Spergel, said every time we build a telescope that has an order of magnitude better in some parameter, some detector sensitivity or size, every time we move an order of magnitude, we discover something totally unexpected, right? So, okay, maybe we can't even phrase totally unexpected in the Bayesian fashion, but let's just play the game. So, particle physics, 99.9% believe Higgs boson exists. Astronomy, let's say we have, like, we're not quite sure whether some, the quasars are of type 2, right? So we think there's, we have two theories of quasars, and, maybe we're 50-50 split between them. So, the outcome of an experiment, we can choose to do one of these two things. We can go build, we can spend billions of euros on the LHC, and when we do that, when we do the experiment, our prior about the Higgs boson will update. And it will update depending upon the outcome of the experiment, right? Similarly, right, or rather, sorry, what we can then do is take, for any particular outcome of the experiment, we can measure the extent to which our expectations were violated. So we have some theory of the world described by this probability distribution over theories in the physical sciences. We do this experiment, we update our beliefs, right? And then we're going to be like, okay, KL is this thing, so like oomph, right? Like how much did my model update? How wrong was I, right? So every particular experimental outcome will have a different kick. We're 99% certain that the Higgs boson exists. So if we discover it doesn't exist, we're going to get this huge boost, right? Our models have to be radically revised. Physics will change forever. The only thing is that our prior is so strong that, in fact, the chance of getting that big pattern break, that big knowledge-gathering boost is really small. So what we care about is something like, let's say, the expectation value of the Kullback-Leibler. Right? So we began with this idea that people want to be surprised by the world. They want to go out and find their models broken. So this is our new F of instead of F being F of P and U, it's going to be F of P, comma, G of P, and G of P is going to be the Kullback-Leibler, and it's going to come in a positive way, so things that have larger KL are going to be more desirable to us, right? So how does this play out? Which detector, LHC or JWST is like the new telescope they want to build. So this would be the thing that would test the quasar theory, this would be the thing that would test the Higgs boson theory. Which one do you build? Which one is going to give you the higher Kullback-Leibler divergence? I'm going to put one more thing in, which is not just the update feature, the extent to which this tells you about this, but also the reliabilities, right? So I'll have two parameters. One is my prior distribution over Higgs versus not Higgs, quasar type 1 or not type 1. And also the reliability, so the extent to which a result here changes this. Here's where it works. So these are your indifference curves. This is exact stuff. So on the x-axis here is your precision, and in this case it's the precision of the telescope. So as you move Along this axis, the decisiveness of the experiment gets higher and higher. Over here is your prior on the quasar story, right? So down here you have really weak priors, you have no idea. Up here you're totally certain. I've set the LHC, like the LHC is going to be a very reliable experiment, so it's high in precision, and it's also going to be testing something we're pretty sure is already true. Okay. Here's the region where, if you're trying to maximize KL, you choose the telescope. So you tend to like things, you tend to like to test theories where your priors are weak, and you tend to like to do decisive tests. So we're predicting now, we've made a prediction for human behavior that talks about the ways in which people might value the breaking of the patterns they've encountered so far. If you have the theory that people hate to have their patterns broken, and we'll counter that in a second, you just flip these two icons. Yes?
There's an issue where you take the mean of the KL, the mean is taken with respect to the distribution of the outcome, which you do not know.
The mean is taken with respect to your priors. So you're like, okay, given my priors, what kind of outcomes do I expect? Given that particular outcome, how will that change my priors?
No, the mean is taken with respect to the distribution of LHCI.
Yes, LHCI.
Yes, but
yeah.
then to have a prior on that is already saying that I have a prior on the outcome of the observations.
Yes, which is that. So this, okay, one thing you need to know is, let's say the Higgs boson exists, what's my detector going to do? So you need to know that as well. So that's the precision of the experiment. So in order to get LHC, like you want to know things like this. So you want to know things like this. What's the probability that my collider will say, yes, there is a Higgs boson, given that there is a Higgs boson? So in order to compute, let's say, the average KL, you'll need to know this.
What are the choices for I?
So in this case, it's binary. So the LHC says yes, the Higgs boson, or no, the Higgs boson. But that could be an inaccurate thing. Like there might have been a malfunction, it might not be sensitive enough, something might make this unreliable.
I think that itself is a problem, because well, you can phrase it this way, but if you just look at what is going on, Higgs and LHC being the two variables here, the expectation is taken with respect to LHC, the marginal distribution of that.
Yep.
Which you could compute by having the prior on Higgs and also, but that is a prior there, right there.
This
here that goes into the computation, so it's circular.
Okay, so let's take it real slow. So here's Kullback-Leibler.
Yeah.
And that's a function of experimental outcome.
Yes.
So what I want to do is average this over the experimental outcomes.
LHC, yes.
Yeah. So I take that quantity there. Now in order to do that averaging, I have to know this quantity here. The probability that the LHC says the Higgs exists, conditional upon the Higgs existing.
You can either know this together with Higgs, or you can know the marginal distribution of LHC. Either way is fine.
Yeah. So I got this and I got this, right? So I can know this without being circular, right? I have a theory of how my detector works, right? I know, let's say, how the little sensitive cells ring when they get hit by an electron,
so
that
if
kind of
that
thing.
is the case, if you take this as given, which I am happy with,
Yep.
but then this KL is still integrated with respect to the prior.
Yes, exactly. Yeah. So what you do depends upon your prior, depends upon this, and it depends upon how good your experiment is.
But how could that, but then your decision is still dependent on the prior, and then all of you're trying to do is to change it.
Yep. And that makes sense, right? Like, I choose experiments to do, let's say I'm somebody who likes to be surprised, right? I'm choosing to do experiments that are going to be sort of surprising given my priors, right? If I'm totally certain about something, I may decide not to check it. My prior is going to dictate part of what I'm going to do.
I'm saying that whether you're making the right decision of choosing the one that would change it the most likely depends on your prior.
Yes, exactly. But when you say right decision, okay, who knows what the right decision is?
Right being the one that's, for example, maximize the mean KL. But
Yeah.
the mean is...
Yeah, so this is, okay, this is what you're going to do, right? You might be wrong. This might not actually be what's going to happen, right? But given your subjective beliefs, given your belief states, this is the region here that you think will maximize your mean KL.
The minimum KL does not depend on that.
The minimum KL also depends on that, it turns out. So the yellow line here is if you want to maximize mean KL. This blue line here is if you want to maximize the minimum KL.
Right, it does not depend on, it depends on P Higgs only through KL function itself.
It depends on P, yes, exactly.
But that's different because you did not average over that.
Yes, exactly. So the mean involves taking an average, and maximizing the min doesn't involve taking an average. So those are two things.
I think they're conceptually different just because
Oh, absolutely.
you have judged the mean also according to what you believe, whereas the minimum, the judgment itself is independent of.
Absolutely, yeah. They're not just conceptually different, but they make different predictions for behavior. So you see the blue line here is if you're somebody who likes to maximize the minimum KL. So you're kind of risk averse. You're like, okay, Christ, what if the worst outcome happens? I get the really boring answer. What's that KL? So this is sort of the risk averse person. This is somebody who likes to gamble, and so they're kind of more interested in the mean. So you get slightly different predictions for what the person's going to do. Okay, you can keep pounding me if it and see if it makes sense. Yeah.
No, I think you explained it very clearly. I'm just trying to think if whether that as a criteria makes sense, because so far it's a little mind-boggling that there's this double sort of dependence on P.
Oh, that you have. Well, so there's your priors. There's what you believe about physics, and then there's what you believe about engineering. So those are the two. You have two kinds of beliefs here.
No, I'm totally fine with the first line.
Oh, okay.
It's the second line that is used both to compute the KL, which is the thing that you're trying to use as a judgment.
Yep.
And also the fact that it has been integrated over the prior.
Yeah. So it is a little weird. No, it's true. I mean, it feels a little weird. The reason it's not totally trivial is that KL kind of does something wacky here, right? It kind of scrambles this a little bit, right? So you're not just sort of putting in the prior and taking out the other side. Like this is a totally nonlinear function. But let's keep going and see if this makes any more sense. So actually, unfortunately, this is the slide that will make the most sense because here's another story about epistemic drive. So this is one that comes out of this guy, Karl Friston, who has something called the free energy principle. So we were very interested in this. There's even an article in Wired about Karl Friston, and it's totally fascinating. The papers he writes are totally fascinating. He's written dozens of them. Everyone's really excited by them. They have this is like a figure, right? So you have he's trying to explain, how the world works. He has this theory about, and I'll tell you what the theory is. He has this theory about epistemic drive. He's the guy who says we can actually go all the way down to the biological and biochemical and physical levels. We can explain everything through epistemic drives. Here's a figure, kind of figure that shows up in Karl's papers. There's a snowflake, and then the snowflake grows wings, and then also maybe it turns into a water drop that's holding an umbrella. So we worked on this. We really couldn't make sense of these papers. They seemed really, really promising, but every time we tried to do a calculation, something sort of went wrong, and then there'd be another paper that maybe made more sense. We couldn't keep track of it, but. One thing that he's very clear about is that he says adaptive systems, so systems that are likely to persist, must minimize surprise. So effectively, and it depends how you do this, right? But there's some model of the world you have, so that's an epistemic state. Now, for him, an epistemic state could be literally the position of your flagella, if you're the concentration of some chemical inside your cytoplasm. So he's got a very broad notion of epistemic state, and he says basically you want to minimize the surprise of the current environmental variable. And you have this freedom, which is that you can take actions. So what you do is you have a model of the world, and you're taking actions, and when you take those actions, you're updating your model, but you're also getting these kicks, right? And the kicks are hurting you in as much as the action is surprising. So very roughly speaking, right? Don't encounter conditions you consider unlikely, right? Or, roughly speaking, minimize KL. So like, for Friston, everybody's the anti-scientist, right? The scientist, that story is somebody who wanted to maximize either the average KL or the max or the min. For Friston, it's as far as we can tell, it's the other way around. And with this, he has this story of a perception-action loop. So we have models, we take actions, the actions change our inputs and also update our models and so forth. So we really couldn't figure out what was going on. We did our best. There's some beliefs Q the organism holds. There's some P that they encounter in the environment, like this is your model of dad, and P is whoever you're actually playing the game against. Minimize that. This is acknowledged by Karl and his collaborators that whatever this theory means, it has this thing that they call the dark room problem. If your goal is to minimize KL, if your drive in life is for your priors to be satisfied, your models not to be broken, imagine you're in a dark room. Why would you ever leave the dark room? Dark room is safe. Your model is constantly validated. It's dark and it's quiet. Why would you ever open the door and walk out into the real world?
Because it's driving you nuts.
It's driving you nuts, right? You know, it's like, because you actually, maybe your drive is the other direction, right? We're trying to settle some real basic questions, right? Like, let's introspect, right? So for Karl, it's like, this is a problem for them, and they have to go into these multi-level explanations to cash it out, right? So they say, oh, you know, if you're in the dark room, yeah, at some high level cognitively, it's not surprising, but you know, you're going to start to starve, and your body will become disorganized and less predictable. And so he has to do some level crossing. He can't stay entirely within, let's say, the space of cognitively accessible states. He's got to go between levels. I don't like that, right? I don't like to. In some sense, it seems to be sneaking utility theory in the back door. So, and I also feel like I leave the dark room not because I'm hungry, but because I'm bored, right? I feel like I have curiosity, right? I want to know things. So anyway, that's a problem for Karl. But it's up in the air. It's nice at least that we can all agree that something like some logarithms are involved. Here's the final one. This is from a machine learning paper, so Zach turned me on to this as well. So Super Mario Brothers. One of the games that you play, metagames you play, is like, let's build a deep learning artificial intelligence machine that is really good at playing video games. Because video games can run on a computer, and the computer can thus run them really fast and learn really quickly. So take Super Mario Brothers, and this machine, right, this algorithm, its goal is it has some model of how Super Mario Brothers works, and its goal is to take actions, tell Mario to do things that it thinks are most likely to break its price. So this is the anti-Fristonian, right? Get Mario to do things that lead to surprising outcomes given your current theory of Super Mario Brothers. And it works incredibly well. So you can actually watch the video, and it's an interesting video to work. So this is kind of like, this is sort of the LAC versus astronomy version. So here's the gang. It's OpenAI and Edinburgh and Berkeley, and they sort of say explicitly what the point of this talk is. As an alternative to shaping an extrinsic reward, is just to give dense intrinsic rewards. So they kind of come at this. They don't have this weird political opposition to utility theory that I guess I have. They have a separate kind of problem, which is Super Mario Brothers. If the only utility you really have is did you die or not. And I guess at the end of the game, at the end of each level, you get a score, right? So you have some set of external rewards, but they're pretty rare, actually. They're not that common. It's a little bit like the poverty of stimulus problem for Chomsky, right? If I'm just getting spanked, I can't do this because I'm attached to a microphone. If I learn language by just desiring not to be spanked, right, I don't get spanked enough, right, to really learn. So their reason for going to this is simply that in many cases when we're trying to learn something about the world, we can't simply have pain minimizing desires, right? And they stick this in, and if you watch the video, it's quite fun, because the way the machine plays the game is it's not trying to maximize the number of coins it gets on the level. In fact, it actually kind of skips a lot of coins. And it skips a lot of coins because that's kind of boring, right? It plays the game that probably you played the game when you were younger, when you weren't trying to like beat your friend, just when you were like, oh, let's play Super Mario Brothers, right? It kind of, yeah, gets some coins because that opens up new avenues and possibilities for you. It likes to eat the mushroom because it gets bigger and it gives you new powers so you can learn more about the world. But it's funny how it plays the game. It's not like the speed run, max score outcome. Does this work in the real world? Well, this could just be a testament to how great the designers of Super Mario Brothers were, right? If this is satisfying, what they've done is they've created a game where the best way to play the game is to be surprised. So maybe they're just great game designers. So another way to say this is the world a good game, right? Is the guy who designed this world, like, did he design it in such a way that the best way to play is to build models of the world and do your best to break them, to be curious? So it is actually, if you look, people who study game design, Super Mario, the original game, is actually an incredibly good example of a game where you can play it without really having to learn. You don't have to read a manual. And in fact, a very young child can do it. It gradually introduces you to the complexity of the world. So there is certainly an extent to which this is a good game. And the question is like particle physics or economic life or the world as a whole, is it also as good a game? Or is it a good enough game that this kind of epistemic drive gives us a really good handle on what people are actually going to do in the world? If I think about this myself, right, I mean, there's the addiction example, right? Like, I don't want to get addicted, right? Even if that addiction will give me the greater pleasure than I would have. Go on, sorry.
In the Mario Brothers game,
yeah,
this is good at, what does this method accomplish?
It enables the machine to play and win the game. And with very little inputs.
There is a winning rule at the end of the story.
Yes, so at the end of each level, you've either died or not died.
Yeah.
And it turns out that if you do things that are kind of surprising you...
shifted over to what people actually do.
Yeah.
But there we don't have a winning rule.
Well, exactly. That would be my claim, right? Yeah. But if you're a rational choice guy, you do have a winning rule. It's the utility function, right? So here it's like, maybe the right way to say is that we're impressed by this because it learns to play this game, right? And it learns to play the game without being told, at least without being told very strongly, that the goal is to win. It happens to win. Mario happens to survive, even though Mario's not trying to survive. It's doing something else. So that's an outcome. If you think like, okay, kind of mix the cognitive story with the evolutionary story, it says if the world is a good game, if we have epistemic drives, we're actually going to make it out the other end. It may, of course, be the case that we just have these as free-floating objects. Right? The example here is in part just to show how people are, in this case, actually driving behavior by giving utility or by getting rid of utility. So they're not just predicting behavior as we did, let's say, in the particle physics astronomy case, or of course in the analogous story where instead of particle physics and astronomy, it's like, is the coffee there, or what am I going to find if I go home early, that kind of thing. Can we really get rid of utility, right? So there's the addiction story, if I sort of go back to where I was a moment ago. Would I really take a drug that would give me an enormous amount of pleasure, far more than I could integrate over my lifespan, at the cost of like turning me into a drug addict? I don't think so. And I don't think you guys would do it either, right? Like sort of on introspection, right? If I were to give you the option of this totally awesome utility function, I don't think you'd take it, right? Another way to approach this is to say, oh yeah, well look, people like to get rich, right? So money has some utility value. Well, another way to say it is maybe people want to get rich because it opens up the possibilities of discovering new things about the world, right? Maybe the reason people want to get rich is they go on a trip, right? Maybe the reason people want to get rich is they can buy a car so they're not always sitting at the bus stop waiting for the bus, right? So even though we might appear to have, like somebody goes into a negotiation with their boss and they don't say, I want my job to be more interesting, they say, I want more money, right? This may actually be an expression of a more basic epistemic drive. And again, that will actually make predictions about the world, right? It will say that in situations where more wealth is more easily able to open up possibilities for discovery, people will desire wealth more. So there's a lot of ways to fit this all together. All right, so I don't know how good a case I've made. I made a case for the fact that our brains are constantly confabulating. They're constantly telling stories based upon strong priors. I've said that's an issue because it means that we tend to ignore things that violate those priors. And then I've told you that maybe that's actually what drives us, right? What might drive us is the extent to which our priors are violated at each point in time. We may choose the actions that we expect to maximize this quantity. Either the max of the min, let's say if you're risk averse, whatever that means, or the mean, or the log of the mean if you're Ole, right? Whatever you're trying to do here, right, is something that depends, that doesn't have this dualistic second fluid, this additional thing that you postulate over and above a knowledge state. All right, so I'm going to give you some examples in the empirical world. These are sort of more fun. These are not lab examples, so this is sort of the data science of human behavior. I am happy to go at it about the claims before we go here. Yes?
So one more thing about the stew theory.
Mm-hmm.
So you have F taking P and some G of P.
Yep.
And say G of P could be one of the KL entry functions.
Sure.
Maximizing this or minimizing this.
Mm-hmm.
But in terms of explanation for why this is the correct theory, say in contrast to utility theory, the benefits seem to be that, well, this flows from the epistemic side, so it's monistic,
Yep.
rather dualistic.
Yep.
And so in some sense, there are fewer adjustable parameters in the theory than the original P theory with P and U functions. Is that right?
So that's one justification, right? There's a, if you come out of a sort of normative theory of what science should be like, right? You may be like Popperian, like how could we ever disprove utility theory? We can certainly disprove these theories. We just, we watch people either obey them or not obey them, right, to some level of accuracy. But utility theory in its broadest sense could never be disproven, right? Problem. We might say that it can explain everything, but you have this sense of overfitting, right? So every different scenario requires this finely tuned utility specification that, yeah, it works within this particular context, within this particular lab experiment, but it's not going to replicate if you vary any of these quantities, so there's an overfitting story. You might have a parsimony story, so even though it's not overfitting, so even if it generalizes well, there's so many parameters that the thing seems really ugly for some reason, so it's more of an aesthetic, aesthetics or kind of an Anselm argument, right? It's like, let's make this simpler, right? So those are a couple justifications that you might have. There's, I think you gave me one, just kind of trying to broaden it out. There's a kind of deeper thing here, which is, well, why did we reject dualism in the end? Right? Why did we go from dualism to monism? There was something sort of incoherent about dualism, right? But the idea that there were these two substances that had there was some fundamental difference between them, and then you say, well, how do they interact, and how is this compatible with what we know about a materialistic worldview? In this case here, it's not a materialistic worldview, it's a cognitive worldview. But we have these things that we believe about the world, and then we have these kind of externally imposed desires. But how do these things interact? Like, can I choose my desires? Where do they come from? You could kind of maybe bake them in a little bit, like you could say, well, evolutionarily this or that, right? So we can bake in those drives, and you can push that as far as you like. You get into this, sort of pseudoscientific evolutionary psychology stuff, right? Why do I want to build the LHC? Because it increases my fitness, because I attract better mates, whatever the story is. That's kind of rubbish, obviously, right? Or you sort of have this, you either have you've got to hard code them, right? You got to get them from the material world. Or, you end up in the Ashabar position, which says, oh, no, actually desires are also cognitive states, and we potentially have access to them. But then you get into this weird Lebowski theorem situation, where it says that, you know, the greatest thinkers potentially are going to become addicts. Now, you can stick on top of that a normative theory, right? So we say that machine isn't really intelligent. So that's one way. So, you know, maybe there are scientific, depending upon your philosophy of science, there's some good stuff. There's some good reasons to reject utility theory there. And there's also maybe this kind of larger picture of where utility theory fits into the history of human thought, right? That this really is, we really are Cartesians about human behavior, and we should get beyond it.
Right, so I guess I'm still not quite sure about the argument or the contrast between the two.
Mm-hmm.
So one theory could be,
Yep.
you take a descriptive theory of human behavior
Yep.
that represented by both a p function and u function.
Mm-hmm.
And the u function should be grounded somehow in your knowledge state, your epistemic states.
Yes.
That you should get your utility function from how you represent the world, and there's some norms governing how they should go, right? And
Yeah.
you know, one of them will maybe give you equivalent predictions about what you should do.
Mhm.
That's equivalent to, say, the one with the KL function.
Yeah, great, great. Yeah, so that would be a monistic theory. If I understand you correctly, that would be a monistic theory,
Right.
right? That would be a rejection of rational choice, which is a fundamentally dualistic
I
theory.
don't think it's compatible with rational choice theory.
It's-
In the sense
it's-
that everyone believes that you should base your preferences, you should base what you value based on what you know, right? And based on what you believe to be the case. So I shouldn't just kind of go around assign utility to everything. I should say, okay, what kind of things are what kinds, and laws of nature, mechanisms, social structures, and so on. Given those knowledge, given those epistemic states, and then have a theory of assigning utility. You and I might disagree on the details, but we probably agree on most stuff, like killing babies is less preferable to, you know, protecting babies and so on.
It would be, I mean, that's a great story, and I tend to agree with you, but that doesn't seem like what rational choice is about, right? So, for example, if that was how rational choice worked, like think about Alban's agreement theorem, right? Alban's agreement theorem, okay, if you're total Bayesian, right, it means that if we have the same priors and we tell each other our beliefs, then we will land in the same epistemic state, right? So that means that if we share the same beliefs, we also, according to this model where utility is derived entirely from our epistemic states, that if we shared the same beliefs, we would share the same desires.
In the long run, very long time.
Well, yeah, but right. So that's a strong prediction that you made. That's in contradiction to rational choice, right? Because if there's nothing that comes in from the outside, then if it's purely the epistemic states, then in fact everything else is going to be the same about those two agents.
Yeah, I agree that it's incompatible with the completely subjective utility theory.
Yep.
But one can have an objective or one kind of a epistemic constraint theory in which, you know, you have your u function, you have a p function. Well, I don't have a story of how you generate the utility function from your epistemic states.
Yeah.
But every reasonable person, or most reasonable person, should agree that we base our preferences based on our beliefs somehow, right?
I mean, it's like, if you're a rational choice type, if you're a microeconomy type, right, you say, you know, our desires begin with our belief states, but they do not end there. I think that's what microeconomics would tell you. And, you know, just watching what these guys do, I see they always postulated utility. They stick the utility in, right?
Of course,
so
yeah,
maybe secretly they have, like, in their pocket, they have this, like, G function they haven't told us about, right? There's always this distinction.
I think there's maybe a way to converge, a way of converging between your proposal and the one version of the EU theory. Namely, that you think about the U function as could be grounded in some kind of epistemic basis. But it doesn't have to be. I mean, the way that people do microeconomics or design theory is to posit as two independent variables.
Yeah, I just don't think they're independent. I mean, like, let's take the mind-body problem, right? This dualism, so let's do the parallel, right? So you got this dualism, and then, you know, Henry Putnam shows up, or Jake Cameron, I don't know, right? And they're like, that's supervenience, right? No check, so okay, let's do supervenience for rational choice. No change in utility without a change in belief state, right? That's a big, deletes a whole chunk of rational choice, right?
Right.
You know, maybe we'll become functionalists, right? But what we're certainly going to do is not say that there's independent desires. There's some current of desiring that runs independently of knowing, which is what has to happen for the rational choice to go through. Now, it is true, right, that I can be a rational choice theorist if I just say U is G of P, right? I can always do that, right? I would say, the way I would put it is, in order to make rational choice scientific, you have to constrain that, you have to throw out this independence assumption. And once you do that, you're no longer really doing rational choice, right? You're doing something else. You know, depends like how you want to market it, right? But I think there is a fundamental leap to go from Descartes to a Spinozist behavioral science. All right.
I'm curious if you've entertained the idea of getting rid of the Bayesian.
We're animals, we just want. That's,
no, well, you can get rid of utility theory, that's fine with me too.
Oh, okay.
But while you're at it, did you entertain the other side? As far as modeling the epistemic state?
Yeah, so the short answer is no, right? There is something that I've been struck by. So one direction this talk sometimes goes, and I didn't show you this slide, is what's called the interface theory of perception, right? The interface theory of perception, it takes those optical illusions that I showed you and the blind spot stuff to the extreme, and it says, look, there's no reason for your brain to represent the way the world is, right? There's no reason for it to give you an accurate picture at all. What it's got to do is it's got to give you affordances that enable you to survive. So in the interface theory of perception, it's the difference between your desktop and the transistors. So from our point, it's like when you boot up Microsoft Windows, it's like, oh, there's files and there's folders and there's a desktop. None of those things are real, right? Only in some very rough way are they models of what's actually going on, which is these transistors. And from the point of view of the interface theory of perception, it's entirely based on an evolutionary model, right? Where the world is being represented in ways that might be complete confabulations. They might lie about causes. They might lie about correlations. The only job is to get us to do the things that we need to do not to get killed. So that would be, in some sense, rejecting the P and sticking in the U. I don't know what would happen if you got rid of both the P.
Well, I guess what I should clarify, zero in a little bit, which is that I guess as far as I can tell, just like you don't have access to this U, and this utility kind of comes out of thin air. I mean, this credence function isn't really something that you have access to either in most cases.
You were pushing, yes. I mean, in your response to Eddie there, when you were talking about this agreement theorem, that's kind of pushing this P to a pretty fantastic.
Yeah.
So your tone inspires, I think, Harry's question. You're really pushing that along. You're pushing that pretty far.
Yeah, I mean, I don't believe Alman's agreement theorem. It's just, okay, if you believe that, you got to believe this other thing. I don't believe either. But take Karl Friston. So in some sense, I said I can't make sense of his papers. One of the nice things about Friston is that he actually doesn't. The inputs to the organism are not probabilistic. They're just events, right? So the organism could encounter rare events. And in that case, what the organism is doing, the organism could, there are some trajectories to that organism that it ends up believing things that are impossible, or rather acting as if it believed things that are not justified in a Bayesian fashion. Right? So I'm not sure, then we can't quite make sense of Friston, because in other places he seems to actually give the organism a model of the world that gets updated. So I can't quite make sense of that. I mean, are you suggesting a more heuristic model of cognition? Is that sort of a mechanism, process model?
No, I don't think so. I mean, I'm really just kind of asking you just what kind of things you've entertained in that. And maybe I'm wrong on this, but I think it's true that it's hard to, I agree that it would be hard or even impossible to falsify anything that involves utility theory. But couldn't you similarly make it, I mean, I know there are constraints on what probabilities have to satisfy, but beyond that, this Bayesian picture is pretty permissive in that you can hold whatever beliefs you want to hold. So if somebody does something, you can say, well, they must just have this.
No, that's very fair, right? That you know, we've cut the parameters in half, but that might not be enough, right? We might still have the overfitting and the generalization problems. The nice thing, I think, like maybe the things you get is that we have some ideas about belief formation that are reasonably rigorous, right? So we can ascribe beliefs to people based on their experiences in ways that seem to generalize pretty well. But we don't have a similar ability with the case of utility, right? So I can tell you how you form beliefs about apples and oranges. If I know how you form beliefs about apples, pretty much I know how you form beliefs about oranges. If I know you like, form beliefs about apples, I know how you form beliefs about oranges. If I know you like apples, I really don't have any idea if you like oranges, right? I have much fewer constraints. It's true that I could stick bizarre beliefs into your head, right? And thus give you strange accents. And you know, it's true. So, you know, a lot of us bought into the Bayesian account of cognitive science, right? Let's model the human psychology as a Bayesian story. To me, that seemed really nice and parsimonious. Funnily enough, when I talked to some of my colleagues, like Peter Todd or Rob Goldstone, they sort of give me the opposite. They say, man, you can just do anything with this Bayesian stuff, right? You just put you put the beliefs you want in, and then you get something out. And we really want these process models because they feel much more constrained. So, although I feel that the probability story, like I'm more constrained in what I ascribe to you, a lot of people are sort of more on your side, right? Hey, maybe we haven't cut out enough yet.
Are there anthropologists in your group? It would seem like they would see cultural differences that don't seem to have anything to do with belief or desire. It's just how you just organize how you do things differently.
I mean, okay, so having epistemic drives doesn't mean you satisfy them perfectly. And it doesn't mean that the actions out the other side are unique. So you can have a multiplicity of behaviors given the same drivers. You flip it around and say, you know, one of the things that's coming out of anthropology, particularly this sort of synthetic stuff that we used to do at the Institute, we do at the Institute, is actually there's some bizarre similarities across cultures, right? There are actually really similar parallel structures for how people organize things. We have the statistics, let's say, of how cities work. That's a great Louis and Jeffries story. So, you know, it may be the case, we certainly have a sense that cognitively we're pretty much the same. Utility seems a little more flexible, but maybe in fact, the fact that we see patterns that generalize across cultures tells us something. We see curiosity as an invariant feature of human behavior.
I'd be curious if you have some empirical stuff.
Oh, yeah. So, I mean, this is, and we'll go through this a little bit, right? So, we spend a lot of time, I do a lot of work where I just go out and measure patterns in the world, right? I look at cultural processes, I measure the patterns, I build some Bayesian model of them. And I look for moments where the model breaks. And out of that, I'm interested in, okay, like, that's a point where there's like, if there is an epistemic drive, something's gonna happen, right? I don't have to plug in some utility, I don't have to sort of infer what people want, I just say, whoa, when the model breaks, let's see, right? So, pattern making, pattern breaking, imagine you have some cultural process. So, you know, some stuff you do, let's say text, we do a lot of natural language processing. Let's say you're writing some stuff at time t, you're doing philosophy in one way at time t, you're doing philosophy another way at time t2, and so on. If we are able to quantify the pattern, so build some Bayesian model, let's say, some probabilistic model of how people are doing things, and we look at how that goes from one step to another, aka given the text or the process I've just encountered, how surprised am I by what comes next. We call this novelty, so this may be, if this is the Super Mario LHC story, then this may be an epistemic drive. We first did this in a paper studying Charles Darwin, so this was Jamie Murdoch and Colin Allen, where we looked at Darwin as having epistemic drives, looking for ways to break, and his reading habits to break the patterns of what's come before. And we find ambiguous results. So we find Darwin, for example, moving between a mode that is more or less driven by the desire to maximize this surprise. We, of course, our model is high level, so we don't have Darwin's model of the world. We have some sort of approximation of the kinds of things he's encountering. So we played a game. So novelty is, given this pattern, how much is that pattern broken by what comes next? I worked with Alexander Barron, who's a graduate student, was a graduate student in Indiana. So both of us came out of physics. We did the natural thing. We said, okay, let's not look at the forward epistemic drive, but let's look at the backward one. So let's look not just at the extent to which this is surprising given this, but let's also look at the extent to which this is surprising given this. So if I break the pattern from what's come before, that's novelty, right? That's some surprise. The question is, what's this one, right? If this is high, if that surprise is high, what does that mean? So the joke is, right, okay, if I'm surprising given the future, if I have high KL given the future, it means that like I don't look like the future. So you go to your department chair and she tells you you don't look like the future of this department. This is not going well for you. So we called this transience. So the time reversal of novelty is transience. We first played this game with speeches in the French Revolution. So there we're looking at how people responded to high novelty. Here's a simple one that's, we've never published this, but this is a story that comes from physical sciences. So this is looking at how scientists are working day to day. We took all the papers in string theory or high energy physics. They're all, fortunately for us, on open access on what's called the preprint server. So every paper in high energy physics that's kind of a player in the game is put on this server. Every morning, people wake up and they read it. Here's an example. Jean-Luc actually was an old friend of mine when we were at Cambridge together. So his paper was at the top 2 days ago. So here's his paper. What we're going to do is we're going to take all the papers and we're going to model them. We're going to build some natural language model. What the model is, not super important. But if you like, you can think of it as a probability distribution over word patterns. So it's some model. Is it, it's a generative model. Can you use it to construct a paper? No, right? It's kind of a Markov chain story, but nonetheless, let's say it's an approximation. It's capturing some gross patterns in what's going on. So what we're going to do is we're going to take each paper and we're going to measure its novelty. So we're going to look at the extent to which it violates the expectations of the past. And we're also going to measure its transience, so the extent to which those patterns fail to be preserved into the future. Each of these dots here, each of these green dots is a paper. The x-axis is that KL to the past. The y-axis is the KL to the future. What pattern do you see here? Right? Using my advanced data science. They're strongly correlated. Things that are novel are also transient. Right? This is actually a big deal already, right? Maybe it's obvious to you, but most people have some kind of folk theory that says people want new things. They get bored, right? So that somehow, the new thing should be preferentially selected going towards the future culturally. So maybe this should bend over. It doesn't. We've never found a system in any culture, in any data set, where there's not a strong correlation like this, right? This is, you might call this like the first law of surprise. Like, culturally, new stuff is thrown out, right? What is new is quickly forgotten. What hasn't been seen before won't be seen much again. If your friend, if I guess you guys are philosophers, if your friend's like, I have the philosophical theory that's going to destroy everything, no one's ever seen it before, chances are it's not going to succeed. This is the John Locke version. People are not so easily got out of their old forms as some are apt to suggest. The analogies go on and on and on. Certainly to biological evolution, right? If you're a farmer and you go out there and your horse has a foal and you're like, wow, I've never seen a foal that looks like that before. This is not going to live that long, right?
So this model is just looking at what words are used?
So a little bit higher level, so looking at co-occurring word patterns, but yeah. So is this a good model? I mean, the classic thing, are we actually getting anything? I'll give you some reasons to believe it. One of the things we think is, okay, here's what's really going on in the sciences. Here's the word scientists use to express themselves. There's no change up here without large changes down here. So it's not just a supervenience, but actually if up here changes in a strong way, also changes the words. Sort of a simple example, if an evolutionary biologist is debating a creationist, the creationist not only sort of denies the theses of the evolutionary biologist, but they literally use different language. So we can detect the existence of major semantic differences that show up in the word usage differences. Here's our results. Here's the strong covariance, right? This rejection, so this suggests, for example, that we are in fact more like Fristonians, right? We don't want new things. Someone gives us something new, we tend to toss it out. The slope, of course, matters, right? So if it's a slope of 1, then okay, we're perfectly stationary. It could be, it could be higher, which means that we're strongly novelty rejecting. It could be lower, which means we're actually a little less sensitive. But let's do the obvious thing. That's your first law of surprise, right? Let's look at some of the dots that break the pattern, right? So this dot here, it's high KL to the past, but it's way off the trend line. So this is something that survives, right? This is a new idea that is not disappearing as fast as it should, right? Somebody has stuck something into the system. It so turns out that this is where the highly cited papers lie. This is where the papers that dent the field, that change physics lie, right? So there's two things that happen here. One is, in order to be one of these guys, you've got to be high in surprise. So in one sense, we do validate the epistemic drive to a certain extent, right? There's not papers sitting here that are highly cited, right? They're all out here. And they're also below this trend line. So they're novel, and they're also sort of the opposite of transient. We call this resonance, this sort of gap here, right? So, resonance, like this is how you get out of this, right? This is the way the system escapes this kind of Fristonian trap and becomes more like Super Mario. That's some time scale, so that's a 6-month window here. So looking 6 months back, 6 months future. This is like how to get tenure. So what I've shown here is the difference in surprise for the top 5% versus the bottom 95% of cited papers. If you look backwards, highly cited papers are surprising, maxing out at sort of 4 years before, let's say. So in other words, a highly cited paper breaks the patterns of 4 years ago, and it kind of gets this reward 2-3 years later, right? So look to what was being done 4 years ago, break it, and your reward will come 2 years later. So second law of surprise, even though in one sense culture is surprise rejecting, in another sense it's surprise accepting. And different ways to tell this story. One is that we're not capturing, our models are not capturing really what's going on in these physics papers. That in fact, if we truly captured the ideas, we wouldn't see this strong covariance, so this law would not kick in, right? But we would capture this, right? So in some sense, we've misidentified, we've correctly located this guy, but we haven't correctly located those guys. Right? Another thing is there's some other sort of quantity, there's some other magic that's sitting in there that's kicking things off the line. We do the same thing, like you just play this game, right? You're measuring a epistemic drive in all these different systems. It's as if you're sort of back inferring utilities. In this case, we come with a strong prior about what those utilities are. This is our G. In the same way, so this is Alexander, Jenny, and Rebecca. So Alexander led this. So instead of physics papers, we just have speeches. So here are speeches from the Parliament of the French Revolution. Some of them are really boring, so people arguing about the minutes. Some of them, like, fights break out and they argue with each other. We do the same story. We look backwards. We look to, is this breaking with the patterns of debate? And if it is it sticking around? Does it have low transience? Here is our first law of surprise, again kicking in. So this is the distribution of novelty and transience in the French Revolution. It's the same strong high in one, high in the other. And then you play the same game, right? So who here is high KL to the past, who here is novel but low transience, right? Who are the people who are able to inject new ideas into the system? Whose novelty satisfies the drive? Break it out in different ways. One of the things you can do is look at all the speakers. So you take who are the people who are lying in this quadrant versus this, and versus this. And so the fun thing is up there are the radical left. So the people who are, you might say, the architects of what turns out to be the terror in the French Revolution, those are the people who are able to trigger, right, this novelty accepting desire compared with, and this is an interesting thing. So these sitting down here, if you look, these are low novelty people, but they're also low transients. They're sitting below the line. So you can say these are sort of the people who are able to keep things on track. So what they say is sort of not surprising, but when they say it, other people kind of hew closer to the mean. And those actually turn out to be some of the most charismatic people on the conservative side of the revolution. Conservative here being in favor of a constitutional monarchy. That's what.
Do that again.
Sure.
What are they doing? They're low novelty.
They're low novelty. So if you imagine in this room, like a low novelty statement would be just following what I'm saying. They're low novelty, but they're also low transients, meaning when they, so let's say you're low novelty, so you just sort of repeat some of the things I'm saying. When you do that, other people also hew closely. So other people actually stay close to you. You're able, through your replication of the pattern, you're able to influence other people to replicate the pattern. The people here are breaking the pattern and inducing others to follow the broken pattern. The people over here, these are people up here are interesting, right? They're the people who are breaking the pattern but are unable to bring others along with them. And the people here are the ones who are hewing to a pattern, and then unfortunately, like, the discussion changes underneath them. So you can think of these as sort of 4 quadrants that people see.
So this kind of cluster on the diagonal is not an empirical discovery. It's probably or is it just something that is a consequence of your algorithm?
It's an empirical discovery. So it could be the case that the way this conversation worked, or this debate worked, or the way science works, is that when somebody does something new, when somebody's high novelty, we all copy it.
But you can't copy all the novelties. I mean, I guess I'm asking you, can you show us a data set that doesn't give this pattern?
We've never found one. We can certainly construct one. Yeah.
So how do you construct one that does this?
Oh, that's okay. Yeah, we can do that, right? So let's say so here's your probability simplex, right? So any point on this is a 3-component probability, right? P1, P2, P3. Okay, I have to add up to 1, right? So people are sticking things in, right? And so in this story here, if this is where we were before, and someone jumps out there, right? What's likely to happen, in fact, is that people go there. Or, potentially, depending upon the dynamics, people go there. So if somebody leaps, you might say they get ignored, or that leap could trigger someone to leap somewhere else. Those are 2 possibilities that would give you high novelty leads to high transience, right? Compared to if people did this, right? Where no low novelty leads to no low transience. But you can get the other case, right, where, let's say you're here, right? And if you make a long enough jump, you bring the whole system with you, right? So you get stuff like this, so people cluster around. If you're sort of like that, you get ignored, but it's the long jumps that end up sticking things in. So in that case, what you get is you get this turnover. Let's see where the block is. You get this turnover where here's your novelty, here's your transience, right? Something like that. So if you were high enough novelty, you'd actually drag everyone along with you. But we've never seen that turnover. We've never seen like a concavity, a strong one. See little wiggles.
If you were a high enough novelty.
Right, you'd have low transients. There are certainly people, so here's the scatter, right? Here's what we see in all the systems we study, right? There are people sitting here, but the overall trend is this strong correlation. We don't see the quadratic. We don't see a turnover where somebody who's sufficiently crazy drags everybody along with them. I see your intuition, but and certainly,
And you've actually generated different pictures.
So you mean for different systems that we
You've
study?
actually used some kind of you've actually produced pictures that are different than that.
Oh, you mean in simulations?
Yeah.
Yeah, sure, you can do that. I haven't done this particular one, but yeah. So we're looking, one of the things we looked at was not in a,
You'd have to have, not all the novelties can drag people. If there's a lot of novelties, only some of them can succeed.
that's an empirical claim though.
It's an empirical claim that if there are no, that's a if there's a lot of novelties, only some of them can succeed. There's not enough room for them to succeed.
Yeah, so let's say, right, so imagine that whenever your novelty is 10, everybody copies you. Right? If your novelty is 5, they ignore you. If your novelty is 10, they copy you.
I mean, how novel it is.
Yeah, exactly. Like if your position along here is,
They copy one guy, and they can't copy all the 10s.
well, let's say there's only like one guy who does the 10 one once. Let's start there. So only one
That
moment.
was why I made my hypothetical. If there's lots of novelties, they can't all be found.
Yes. Well, it depends what you mean by lots, right?
Well,
So.
but I mean, you're looking at systems where there's lots of novelties. You're looking at revolutions. You're looking at academics who are all trying to do something new. So
Right.
if you're looking at systems with lots of novelties, it seems like this is going to be forced. That's my question.
So the question is this, I think what you're asking is, well, maybe there's two things you're asking. One thing you might be asking is this mathematically what has to happen?
If there's lots of novelties.
If there's lots of novelties. And my claim would be no. You could have some extreme tail of novelties, right, that are rare, but when they happen, they drag everybody with them, right? So that would be a case where you have lots of novelties here, few novelties here, but it's those extreme events that have the impact. So I think, I understand your intuition, is that making sense?
They are. I guess I have a hard time seeing it and would want to see the simulation happen.
Sure. Yeah. Yeah, no, I mean, it's an intuition, right? The case that seems like the simple one that I can see, right, is let's say there was only one high novelty.
I mean, I find it interesting.
Yeah.
After when you look at the pattern.
Yeah.
It's interesting to know who is in the different quadrants.
Who's here? Yeah, exactly.
That's interesting.
Yeah.
But the pattern doesn't seem like such a. It seems like maybe it's not a empirical so much as a. I'm not convinced that the pattern is an empirical discovery. I mean, maybe you discovered it empirically, but it may be more of a mathematical inevitability. It would still be interesting to look at two of the different quadrants. That's an empirical.
Let me give an example. This might drive it. I mean, that's something I worried about, right? In some sense, like, we see this all the time, and you're like, well, maybe this has to be the case. So we looked at the institutions. So, okay, let's go back to the physics one, which is easier because we're all academics. So let's go here, right? So we looked at the institutions, and we say, okay, which universities are here? Which ones are here? Which ones are here? And which ones are here? Right? So sitting around here, or actually around here, is one of my old universities, Indiana. right? So people in physics, some of them, right, not everybody, but people doing physics in Indiana tend to do low novelty papers, so they tend to kind of follow what other physicists are doing. But they're doing solid work, right? So they're doing what other people are doing, but they're kind of picking the right topics, and those topics aren't disappearing anywhere soon, right? So they're picking sort of steady stuff. They're kind of like, you think of them as the conservatives. Sitting up here are kind of these institutions where, unfortunately, the physicists in those institutions are working on problems that everybody's working on, but they're kind of late to the party. So by the time they've written those papers, physics has moved on. So they've done low novelty stuff, but pretty soon afterwards, everyone stops doing it. So those are those institutions there. Sitting up here, you can think of those as the radicals, right? So university like Penn State is up here. So Penn State, you kind of know they do very innovative stuff, but it hasn't quite taken off. Like they do stuff that, for example, is kind of battling the string theory. They're not getting taken up, they're high novelty. Right? Finally, sitting here is the Institute for Advanced Study, right? So this is the sort of highest prestige institutions in the country or in the world. So the question is like, what if you just got rid of Penn State, right? So what if you just dumped that institution? And so the only people doing the novel things were also the super influential people. So every now and again, out of Princeton would come a paper that just changed the field and everybody heard it over to them. Now you'd see this turnover. Okay. So you can, if you dropped all of the unsuccessful novelty events, like if you just tossed them out and you were left with a smaller number of novelty events, the successful ones, you could see this, but we don't.
You don't. When you throw points out, you don't just throw out. You're throwing out both sides of the equation.
Yeah, I see what you're saying. If it's a time sequence like this, right? Actually, I mean, in this case, what we do is we take these aggregates, right? So we take all the papers in the time unit and sort of compare them like this. So.
You're throwing out what they're following as well as who follows them.
Well, we're lumping them in because things that are too close in time don't actually have the ability to influence each other. It's part of it. But anyway, we can. I think this is something we can maybe chat about offline a little bit. So I'm happy to. I mean, we can roll as long as you want, Harry. So.
We can. Well, why don't we continue at dinner?
I'd love that. Yeah.
Okay. Thanks
this
a lot.
is great. I really appreciate it. So thank you very much. Yeah.